Hello everyone, welcome to my videos. I'm Simon. In my last video, I've talked about some stuff related to sequence convergent, and in this video, I would like to continue with this part and introduce some more theorems related to sequence and series. Basically, series is a special kind of sequence. So now let's begin. So the first point I would like to say is called monotone sequence. Let me write it down. Monotone sequence. Basically, this theorem said if you have a monotone non-decreasing sequence. So this means if you have n is less or equal to n plus 1, then a corresponding terms of sequence Sn is less than or equal to Sn plus 1. This is what we mean by monotone non-decreasing sequence. So if you have such a kind of sequence and it is bounded above, then this sequence will converge to its supremum. Well, let me stress a point a little bit first. Namely, this supremum of the sequence is indeed exist. This is guaranteed by a axiom called the completeness of real numbers. If you have a non-empty set of real numbers bounded above, then it has a supremum. It is called a axiom. Completeness of real numbers. So basically, if this set is non-empty, the real number set, non-empty, bounded above, implies supremum exists. Okay, now we are guaranteed that this supremum does exist. Then we need to prove that the sequence, monotone non-decreasing sequence, bounded above, will converge to this supremum, say L. Let's say L. And similarly, if you have a non-monotone non-increasing sequence, that is, if n is less than or equal to n plus 1, Sn is greater or equal to Sn plus 1, and it is bounded below, then it will also converge, no, sorry for that, it will converge to its infimum. It's nearly identical, so I may just write down half of this series and they prove monotone non-decreasing this situation. I may try to write it down. They prove. So we know that if you have a supremum of a set L, then implies L minus epsilon is not a supremum. That is equal to say there exists a n naught such that Sn naught is greater than or greater equal L minus epsilon. Since it is a monotone non-decreasing sequence, then for all n greater or equal to n naught, Sn is greater than or equal to Sn naught. Consequently, we know that Sn is greater or equal to L minus epsilon. And since L itself is a supremum, L is a supremum. This implies that Sn is less than or equal to L plus epsilon. That is for sure. So we can bound the sequence Sn by two definite bounds, namely Sn is which is exactly the definition of sequence convergent. We say that if we have such an n naught for all n greater than or equal to n naught, Sn minus L, the absolute value of this expression, is less than or equal to epsilon for arbitrary epsilon greater than or equal to 0. Then sequence Sn converges to L. We have proved that. And that leads to another important theorem I would like to introduce. But before that, let me just explain or raise up one prelude concept, and that is subsequence. This is the second point. Subsequence. So, as its name suggests, subsequence is just you taking out some terms in a whole sequence, and the terms you've taken out forms a new sequence, which you can then do some manipulations regarding to this sequence. And what is a subsequence then? It is sequence Snk is a subsequence if Nk is a sequence of strictly increasing natural numbers. Natural numbers. Then Snk is a subsequence of Sn. Okay, that is the definition of subsequence. And now I would like to say more on an important theorism regarding to sequence convergent, the judgment, and that is called a bolzano-weiestrass theorism. Let me write it down. So this is point 3. Bolzano weiestrass theorism. what it tells us is that every bounded sequence has a convergent subsequence. If Sn is a sequence of real numbers, such that it is bounded by a finite interval, so we have got a Sn, a sequence such that it is bounded for all n. Then there exists a subsequence converge to a limit L, which belongs to the integral a and b. So now I would like to try to write down the proof of this theorem. So it is divided into roughly two sections. One is that we need to convince ourselves that this limit L is indeed belongs to the interval AB. And then the second step is we need to wisely construct a subsequence such that it is bounded by A and B. And roughly these two steps. So the first point we enter into this problem is that there are infinitely many terms of a sequence bounded by an integral. Let's say A and B. There are infinitely many Sn inside this integral, and we bisect this integral. And then at least one of them will contain infinitely many Sn, because if both of them contains finitely many terms of a sequence, then the whole sequence cannot own infinitely terms. So this is a point. And then you just bisect the integrals. Such that every time you bisect the integral, there are some nice properties to your quantiles. Now you can see that we have constructed two sequences, AK and BK, where AK is a non-decreasing sequence and BK is a non-increasing sequence. Well, the order is it doesn't matter. You can reverse it as you wish. But anyway, the point is that we have constructed two subsequence AK and BK where they have some nice properties. We have applied the first monotone sequence, this theorem, into this provement. Since one sequence is monotone, non-decreasing, and another one is non-increasing, and both of the sequence is bounded, then they all converge to a limit. This is what the monotone sequence theorem tells us. And then there is another point we need to pay attention to. Maybe I should figure out these quantiles. And then we have another property regarding to these quantiles. That is, so another property regarding to these quantiles is bk minus ak tends to 0. And so this ensures that they will tend to the same limit. Since we know that no matter ak or bk, either of them, let's say ak, it is bounded by a and b. So the limit of ak will bounded by this set as well. We know that from this nice property that limit of these two sequence will be L. Then the first result follows, namely, there is such a kind of limit that is bounded by the interval a and b. And then there is just one remaining problem, that is to construct a subsequence which satisfy the conditions being stated in the theorem. And that is not quite hard. We can define, oh, by the way, the first interval being bisected from the original one, we define it as n1. And the second one, we define it as n2, and so on and so forth. So what does this n1, n2 up to nk, what are the properties they have? We give such a definition of these intervals. Nk is a set where n belongs to natural numbers and Sn is bounded by the quantiles ak and bk. So we just squeeze this sequence from originally a to b, and then squeeze it to a1 to b1, and then squeeze this sequence again and repeat the procedure. And this is the definition we give to this set n1, n2 up to nk. And then we can take, for example, because to construct a subsequence, we need a sequence of natural numbers which are strictly increasing. Then we can wisely choose these numbers. For example, we can say n1 is the minimal of n1, and n2 is the smallest n, which is bigger than n1, and so on and so forth, up to nk. And you can see that this n1, n2 up to nk, they forms a sequence. And since n2 is greater than or equal to n1, oh no, sorry, n2 is bigger than n1, and the same procedures repeat again and again, and we have successfully found a subsequence. Then we can define a subsequence as nk, which is bounded by the interval ak and bk. And we have proved in the first section that ak and bk both tends to a limit L. Then this subsequence we have constructed will also tend to L, and this is implied by sandwich theorem, which is a theorem not quite hard to prove. And that is all for bolzano-weiestrass theorem of sequence. And for the next part, I would like to introduce cauchy sequence, which is again in a vital important role. Especially, it has been applied into some judgment to see series whether it is convergent or not, called a Cauchy's criteria. Maybe I will talk about that a little bit later in this video. So now let me first give the definition of Cauchy sequence. Which point is it? Cauchy sequence. It says there exists such a knot for all mn greater than or equal to this n naught. The absolute value of this difference is less than arbitrary epsilon greater than 0. Basically, what we want to show is that to say a sequence is a Cauchy sequence is equivalent to say this sequence is convergent. This is what we are trying to prove regarding to this special kind of sequence. And we divide this proof into 3 parts. Well, let me write it down. We are aiming for proof Cauchy sequence convergent. So the first step is sequence convergent implies the sequence is Cauchy sequence. And we prove this by applying triangular inequality. That is to say, Sn minus L plus L minus Sn is less than or equal to if there exists an Sn such that this is the definition of sequence convergent, and if m and n is greater than or equal to this n naught simultaneously, then these two expression holds at the same time. We can take each is less than epsilon minus epsilon over 2 and add them together. And then we have proved that sequence convergent implies it is a Cauchy sequence. And the second part is Cauchy sequence is bounded. In this part of proof, we need to fix one index in the definition of Cauchy sequence. Cauchy is bounded. We fix, let's say, m is equal to n naught. Then we can see that we apply the same inequality again and again. But nevertheless, it is quite useful. Now, applying the triangular inequality again, we can rearrange the original expression of a sequence to switch it to a form we are more easy to deal with. This is for all n greater than or equal to n naught. We have this inequality stated that Sn is bounded. But what if n is less than n naught? Then it's fairly easy. We just take the maximum of this n naught minus 1 terms. And the last step is to take the maximum of these two expressions. You just put the Sn naught absolute value plus epsilon into this set, and you take the maximum of this set as a whole. And then finally you can say you can see that indeed Cauchy is bounded. So the last step is Cauchy is convergent. Why we do this step first? To prove that Cauchy is bounded, that is to apply our theorems, namely bolzano-weiestrass theorem, into the provement of this new theorem. We need to construct a bounded sequence to use the BW theorem. And now we have successfully shown that Cauchy is bounded. Then everything is done as a prelude. So then we come to the final step. Cauchy is convergent. Since it is a bounded sequence, we know that there exists a subsequence converged to a limit. As nk minus L is less than, let's say, epsilon over 2 for all k greater than or equal to n1. Also, the property of Cauchy sequence itself reminds us that if we have a Cauchy for all m and nk greater than or equal to n2, then Sm minus Snk, again the absolute value of this expression is less than epsilon over 2, let's say. And then if we just take the maximal of this n1 and n2 to satisfy the both conditions simultaneously, then we can finally go to the result we want. Now here we have come to the end of the proof. We have proved that Cauchy is indeed convergent. So we have proved that it is equivalent to say a sequence being a Cauchy sequence and a sequence being convergent. And then there's some fancy applications, namely the comparison test and series converge absolutely. But before that, I would like to explain something regarding to series. We say that, oh no, hang on. Series. What is series? Series is nothing else than add up all the terms in a sequence from, let's say, n from 1 to infinity. This is the series. And we say if the limit of a series exists, then summation from n equals to 1 to infinity ak is equal to limit n to the infinity. You see, we've switched this infinity to a finite n, and let n tends to infinity. This is exactly what we are considering about when we are think of the concept of a limit. And this expression is called a partial sum of a series. So to decide whether a series is convergent is equivalent to say whether this summation n from 1 to n of ak is convergent. And there are some reasons which can help us to judge that relatively handy. One is called series converge absolutely convergent. So this is the oh no, this might not be the fourth point. Let me check. No, this is the fifth point. Series converge absolutely. Oh, I'm making mistakes again. Absolutely if the summation of the absolute value of ak converges to a limit, or and this is quite easy to think about. Let theta n equal to this ak. No, sigma ak. Then theta m minus is just equal to the absolute value of this summation from n plus 1 to n. Well, by triangular inequality, it is less than put out the sigma outside the sign of absolute value ak. And it is convergent, then it is a Cauchy sequence. We denote it as tau n minus tau n minus tau m. Well, there's no doubt it is less than epsilon. So you can see that the original sequence, the original series itself is a Cauchy sequence. So that is equivalently to say it is convergent. We have proved that with no doubt. And there's another series called comparison test. So comparison test. Basically, it says you You want to know whether a series AK is convergent or not, and you compare it with a existing convergent series by some technique, and then you can judge whether AK is convergent or not, the original series is convergent or not. So let me formalize this into mathematical expressions, mathematical notions. If you have a already known series which is convergent, then for some constant m greater than 0, if the absolute value of AK is less than or equal to m times bk, then summation AK series absolutely convergent. The provement of this series is nearly identical to the absolute convergence itself because of the existence of this absolute value of the original series. We just switch it a little bit. This time we denote theta n equals to well, this is one term. Every single term in the sequence, and then if you sum it up, this does not change the original direction of the inequality sign. Let me formalize it. This is how we deal with this series being defined. And it is less than m times summation from m plus 1 to m bk. This is what I have just referred to regarding to this inequality. Every single term in the sequence, it has such a relationship, and if you just sum them all, it will become a form of series, which is again valid since we have not do anything to reverse the direction of the inequality sign. This is valid. And again, this is equal to m times a cauchy sequence. It is then less than epsilon. And we know that, well, this absolute AK, the series of absolute AK, is convergent. And by the first theorem we have derived, we know that this means the original AK, sigma AK, is also convergent because of the concept of sequence convergent absolutely. This is the first part of my last point, 5.1. And this is 5.2. These two shares a highly similar proof to the theorems. And anyway, okay, that's it all for this video. Thank you very much, and see you in the next video.